TTL Computer 2. Today, we're going to take a look at the instruction set that I have defined so far for TTL Computer 2. And we're also going to introduce my solution for instruction set assembler that we'll be using for TTL Computer 2. We'll also briefly look at that. Okay, so let's jump into this. So if you recall, we have up to 64 instructions that TTL Computer 2 is going to support. And what I've done here is come up with different groupings for the assembly statements, and it'll help us to organize our thinking about them. And I also am calling out what flags will be affected by each of these instructions. Okay, so let's start going here. The first set is I'm just calling implied. These are just single operand instructions, right? We have no op, we have clear and set the carry flags, we have rotate left the A register, and the return instruction. And we can see here what flags are affected by each of these instructions. Okay, and the next set is the immediate addressing mode, and we're supporting loading immediate for all of our registers, A, B, and C, as well as the stack pointer. We can load immediate values to those registers. We also have extended immediate, right, which are 16-bit instructions. We have jump if no carry, jump if not zero, jump if carry, jump if zero, and also jump if negative. So if you think back to our first introduction architecture video, I said we were only going to support two flags, C and Z, and I basically made that be three flags. So we will have also a negative flag as well. And then load immediate for the BC register. So we have A, B, and C. Those are 8-bit registers. You can combine the B and the C register to be used as a 16-bit register. And we'll see that some of our later instructions support that 16-bit register. Okay, and then the last of our extended immediates is the call statement. Okay, and then the next group are absolute addressing, and we support that with the use of a 16-bit address for loading A, B, and C register, and also the reverse of that, which is storing of A, B, and C to a memory location. And I've kind of adopted the Z80, I think it's the Z80 instruction set approach, where we don't really have any store instructions. Everything is a load instruction, and we're either loading to a register or we're loading to a memory location. And I like that. That keeps the nomenclature or always going from to the right to the left. The right is the source and the left is the destination. So we see that these loads of the register will update the negative and the zero flags. We have our register indirect addressing, and this is really for the stack pointer, right? So we will be able to use specify a displacement, which will be either plus or minus displacement for the stack pointer to load to register A, or to store to this location using the stack pointer and a displacement of the A register. And again, we have the negative and the zero flag would be supported for the loading of the A register. So I generally only support the setting of the flags for the store operation to the register. Okay, and then is absolute indexed, and here we can use the B and the C registers combined to the 16-bit register BC, and we can use that as an index to a memory location, right? So the register indirect using the stack pointer is really going to be important for subroutine calls to, access arguments that have been placed on the stack, or updating any arguments for return values in the stack. So that's primarily how that's going to be used. And here, the primary view here is going to be accessing of arrays with an index, and that might be like arrays of characters or string arrays as well. Is the view for the use of that instruction. Okay, and then we have a whole bunch of these register instructions, and these are all the combinations of A and B registers, loading them, and you'd think 64 instructions are a lot. It's kind of not that many when you start to put a stake in the ground and putting some real specifics with the instructions. We kind of have a relatively large number of registers that we have that we're working with. So like I didn't do load A. You can't load register A to register A or register B to register B. I didn't implement those. It was just wasting instructions that we can use for something more important. And so these all set the negative and the 0 flags. We can increment, A, B, and C register. And though that sets the negative, the carry, and the 0 flag, we can also increment the BC combination, the 16-bit register. We can also increment that. And the flags for that are negative and 0. And then we have the corresponding decrement instructions for those registers. We get to the add and subtract statements here. Again, I had to cut back the number of register combinations we could use for the additions and basically the operations. We just don't have enough instructions to do add arithmetic and operations on every register combination. Basically, what's provided is again, A is the accumulator. That's the primary register. We can we can do math operations on A and any of the other registers, an immediate the B or the C register. Okay, so that's the same thing for basically all the math operations. Add with carry, subtract with carry or borrow. We have and, or, and XOR. And we see the flags that are set for each of these operations. Okay, then we have our stack operations, pushing A, B, or C onto the stack. Also, we can push the BC combination, the 16-bit register, on the stack, and we can pop those off the stack as well. And then lastly, we have register indirect. Okay, and here again we see that combination register BC, that 16-bit register, can be used to indirectly reference memory. So we can load you can load any piece of memory within our address space into A, or you could store A into any memory location in our address space as well, directly with the load and the BC register. Okay, and then we can also use BC again to jump to any arbitrary location in our address space. So that is kind of interesting just to be able to do that. But what's really in view here is being able to do computed jumps, right? Where you're using an offset to calculate where you're jumping to, right? And that's something that we do frequently in assembly programming, right? Our computed go-tos or computed jumps. And then we have one last instruction left. We have one extra instruction that I'm sure we'll come up with something to use that for. But right now it's just in here as a no-op. So that's the instruction set as I have it defined. I've kind of gone through a few iterations to get to this set, and I think it's again, I'm looking in view to the type of programming we're going to have to do. And I think that what we have certainly will cover and give us a lot of operational capabilities with our instruction set, but these are only microcode, right? This is only microcode changes to implement all of these. So we'll always have the flexibility to change these later on down the road. Okay, so that's our instruction set. And now I'm going to switch over to a related topic, and that's going to be how are we going to assemble these things from source code into machine code that we will, ultimately hex load or load into our ROM as part of our ROM image. And I came across this tool that is really cool. It's called Custom ASM, and you can just search for that on the web, and you'll be able to locate that. And what this is it's a program for defining assemblers, and it's really easy to use, and it seems more than capable for what we need to do for TTL Computer 2. And I'll just briefly show you how this works, and then we'll see this in greater detail when we start actually looking at some sample programs after we get the simulator all up and running. Okay, so there's basically this rule def section where you see we define our assembly statements. Here is just the no op, and this is the opcode value for the no op, right? 0. Here's our load A from B register, and this is the opcode. And so I just picked trivial ones here just to illustrate how this is used. It handles using immediate values, 8-bit immediate values, 16-bit immediate values, and addresses as well. But we'll look at that a little bit later on. Okay, so that's the rule def section for our really dumbed down instruction set. And these are just 2 simple instructions from our instruction set. So here starts the source code of our assembly program. Here's the no op, and then here's our load. Okay, and this is just a web version of the custom ASM that the project provides. We, in practice, won't use this. There's a command line tool. This is a command line tool, and we'll run it from the command line to do the assembly. But this is really just convenient to show you how it works. Okay, so I'm going to press assemble, and there it is. So this is like an assembly listing. We call it an annotated listing, and here is this is the memory address pointer. So we're at address 0, and here's our no op statement, and you can see that's been translated to hexadecimal 00 like it should be. And then here's our load A from B statement, and that's at memory address location 1, right? And here's our hexadecimal opcode for that. So we see how it did the translation. So really simple to use, and really is going to do what we need to do. So it'll save me a lot of time not having to really do all the legwork of building an assembler from scratch. And then what was cool about this too is that this has this logsim format, and I'm going to hit assemble again. And this is exactly the format that we need for our digital simulator program to read these files. So we will be able to, define our our programs that we're going to load, our monitor, whatever we're going to develop, that's going to reside in our ROMs. And we will be able to use this tool and this format to easily load that into our digital simulation. And that's how we're going to get our programs in to the digital simulation, is using this approach. And then it also supports Intel hex format. And looking down the road to when we actually have hardware implemented, and we will need this format, the Intel hex format, we'll need that to load our ROM code, into our EPROMs. We will need to use this Intel hex format. And ultimately, I'll write another hex loader that we're going to use so we can upload programs in real time to the computer. Those will also be in this Intel hex format. So this custom ASM tool is really easy to use. It's very convenient. I've been playing with it a bit, and it's a solution for us to get our programs into our digital simulator, and also into our EPROM programmer later on for our hardware and for our hex load process for our real-time uploads. Okay, so that's that. All right, so what I'm going to do is I will try and post the instruction set to my YouTube website in the community pages. I like to post there rather than putting it into the videos. This way they're all in one place and people can kind of more easily find, any updates or any corrections or details that I put in, or any dialogue we might have, any questions that are asked. Are kind of easy to locate rather than having to go through the videos, one by one and trying to find information. Okay, so have a look in the community pages once I get that posted, and if you have feedback on the register spec, please post some comments. I will look at those. Again, this is a starting point, and unfortunately have to make a lot of compromises. 64 instructions sounds like a lot, but it's not, and they get used up pretty quickly. One thing I also didn't show you here is that we'll be able to implement a bunch of higher order instructions as macros, and we'll probably end up having about a dozen or so of those. These are the ones that I could immediately think of right now, but we'll have about a dozen or so more of those that are macros that we will have available to us in our assembly programs as well. Okay, that's it. Thanks for watching.